Alright everybody, we're back here with the state of the unit here for unit 1. I polled you guys, see what you guys wanted to hear more of. Here's what I got back from you. A lot of you were asking about writing word problems, interpreting these symbols. Now, what's on the screen right now are things that we need to know if we want to have success with it. When we're talking about writing an expression, we want to use this table to the left to know how to write a model for whatever situation we find ourselves in. For addition, we see words like plus, add, sum, more than, increased by. Doesn't matter how we phrase it, all of these phrases come up with the expression n plus 5. For subtraction, you might see the word minus, subtract, difference, less than, decreased by. All of these giving us the expression x minus 11. For multiplication, times, multiplied, product, which surprisingly stumped a few of us on the quiz. But again, no shame in that. Let's just study it and get it locked up going forward. And lastly, division. Divided by, divided into, and quotient being some of the key words we might see. Remember that when it comes to subtraction and when it comes to division, our order is important. 11 minus x is not the same thing as x minus 11, and 7 divided by a is not the same thing as a divided by 7. So we got to look closely at the question for clues and really pay attention to how we're supposed to be setting those up. Next up, these symbols to the right we use to compare two different expressions. We can say the two expressions are equal to each other. One is less than the other, one is greater than the other. And then we have less than or equal to and greater than or equal to. We shouldn't be getting too confused with these. It's really just a combination of something being equal and opening up the possibility for it being more than or less than. Now, a lot of people on the quiz seem to be getting confused with saying something is less than a number and something is less than a number. Pay attention to the verb is here. When we have that action verb, we're really differentiating one side from another. If we're just saying something is less than, we're still talking about the same expression. We're still talking about it in regards to each other. So that's something to be on the lookout for. Let's try an example that really illustrates this. So we have two different problems here. We have 7 less than 3 times a number q is 10. And then we have 7 is less than 3 times a number q. So take a moment, try to jot it down, see if what you get is the right answer here. Again, 7 less than and 7 is less than are our really big changes here. And then on the end here, we have it is 10. Again, if we see something is the same as, that should be ringing the bell for an equation for us. So if we're saying 7 less than, remember that order is important. So we have to say that 3q minus 7 is going to end up equaling the number 10. Now, here, I saw a lot of people, they saw 7 less than first, and they just let off with 7 minus the second part. We gotta be critical readers here. We gotta have these language in our toolbox ready to go whenever we need it. Alright, next up, 7 is less than. That means we're comparing one thing to another. So if we have 7 over here, we have 3 times a number q over here. We're looking for one of these symbols to compare one side to the other. So since we're saying this 7 is going to be less, we got our hungry alligator taking a big bite out of the 3q here. Alright, not trying to move too quickly, but I do know your time is valuable and I do not want to take all of it. So next up, I heard about people wanting to see more about evaluating functions. So here we are given the function y equals 4x plus 2, and we're asked to evaluate it over the domain 0, 1, 2, and 3. Now remember that the domain is our what? Well, it's the input of our function. This is what we're plugging in. This is what goes in for our x's. Some people want to build it up to be something bigger than it is. It's really not that bad. So if we're looking at 4 times 0 plus 2, well, 4 times 0 is of course going to get a 0. 0 plus 2 is going to be what we're looking for as our y value. Now let me take a moment here and jot the rest down for a second. I'll be right back. Alright, got the rest down here. We plug in 1. We have 4 times 1, which is going to get us 6. Add 2 to it, and we end up with... Oh, sorry about that. Getting ahead of myself. 4 times 1 is actually 4. Add 2 to it, and then we get the 6 that I was referring to earlier. 4 times 2 is going to get us 8. We come in, add the 2 after the fact. We have a value of 10 here. And on the last one, 4 times 3 giving us 12. Plus 2 will bring us to the 14 that we're needing to write in for our output. Now, if you're noticing that 2 plus 4 equals 6, 6 plus 4 equals 10, 10 plus 4 equals 14, then you might be starting to realize that there's something called a slope, which we'll be seeing later when we're talking about graphing linear equations in slope-intercept form. So keep that knowledge with you, and we'll be using it in the future. Now, two last things, but they kind of really roll into each other, is how do I break down a large number in prime factorization? Now, of course, in my class we were using this for square roots, cubed roots, any nth root. We wanted to be able to break down the number into its prime factorization and use that to help us find the roots. So there are a couple tricks that can help us get started on this if we really don't know where to begin. If what number is divisible by 2, it's going to be even, basically meaning that the last digit's going to be 0, 2, 4, 6, or 8. If the number is divisible by 3, then if we add up all of the numbers in it, that sum will be divisible by 3, which is kind of a cool property. 4, the last 2 digits of it is going to be divisible by 4. The 5, meaning that it ends in a 0 or 5. 6 needs to satisfy the divisibility rule for 2 and the divisibility rule for 3. It's 2 factors. 8, meaning the last 3 digits are divisible by 8, kind of almost related to 4 here, but we're going one more digit place than what we're looking at. 9, similar to 3, all of the digits added up need to be divisible by 9 in order for something to be divisible by 3. And 10 should be the easiest of all. If it ends in a 0, it's going to be divisible by 10. So we want to take a look and we want to try to apply this to our number 3,240. So right off the bat, let's try to take away as big of a chunk as we can. I see a 0 at the end, so I know that 10 is going to be a factor of this number. Now, what's left over after we take 10 out? 324. And we need to really start looking at, well, how can we break this 324 down? Well, let's try some of the rules here. We do want to try to maybe get as big of a number out as we can. Remember, we're going to the prime, so it doesn't really matter what we start with. They all lead to the same place. Now, adding up the digits, 3 plus 2 plus 4, we're going to get 5 plus 4 or 9, which means that we can either divide by 9 or divide by 3. Now here, if I wanted to divide this by 9, I'd end up with 9 times 36 as my factors. 10's not quite prime yet, so we got to break that down into a 2 times 5. Again, we just slowly work our way down. Now that the numbers are more manageable, the process should be easier. We're looking at 3 times 3 to get us 9, 6 times 6 to get us 36, and you could have gone 4 times 9 if you wanted to, 2 times 3, and 2 times 3. Now I'm going to try to clean this up a little bit and get it in factorization form. So give me a moment. Now that I clean this up a little bit, we can see that the prime factorization is just equal to the amount of primes that we have. So 1, 2, 3 different 2's. So we can write this as 2 times itself. 3 times. We have 1, 2, 3, 4 different 3's. So we're looking at 3 times itself 4 times, and 1 and only 1 5. So our prime factorization of a number like 3,240 would be equal to 2 to the 3rd power times 3 to the 4th power times 5. And why is that useful? It actually helps us when we're trying to simplify for a certain root. Now let's take that and use that going forward. So remember, 2 cubes times 3 to the 4th times 3 to the 5th. And we'll use that down here when talking about the square and cubed roots. Remember that the index, the number outside here above the radical, determines how many times the root must be multiplied by itself to get out of that radical. So if we're looking at 3,240 again, let's plug back in our primes here. We had 2 to the third times 3 to the fourth. That's an exponent, even though it looks kind of like a... we'll leave it as that. Now, as we're looking for the square root. So even though it's not written here, there is a 2. We're looking for something times itself 2 times. So when we break this down, why we have this, well, let's just break it down into things that are squared. So 2 squared times 2 is still going to get us that 2 to the third power, 2 cubed. Now 3 squared times another 3 squared is going to get us that 3 to the fourth power. And 5 is just 5. There's no exponents, no games we can play with it. So we need to be looking at what can come out. Well, here, change colors here. We have a 2 being squared, we have a 3 being squared, and we have another 3 being squared. So that's all something we can take the square root of. The root is saying, well, what times itself 2 times? So that 2 can come out. That 3 is getting multiplied by itself, and finally the other 3 is getting multiplied by itself. That 2 and 5 is left inside. We're multiplying. These are just factors, so we got to put them back together as factors. We have 2 times 3 times 3, or 6 times 3 is 18. We'd be looking at 18 radical 10 as our square root. Now here, we want to take these prime factorizations, same number, same radicand here. We just want to find the cubed root for it now. So I'm going to be looking for something times itself 3 times. The 2 cubed fits in nicely to this agenda. The 3, we have times itself 3 times, and then we have another 3 left over. And then last but not least, the final 5. So when we're talking about the cubed root, how many roots times itself 3 times? Well, this 2 can be a root. This 3 can be a root. Sadly, the 3 and 5 are left behind. So we're left with 2 times 3 times everything that's left inside, or 15. Oh, what's 2 times 3? It's just going to get us 6. 6 root 15. Oh, sorry. I'm forgetting a pretty important part here. The index. Don't want to get it confused with the square root, because we do have, oh my goodness, we do have to be clear on that. So 6 times the cubed root of 15 would be left over. Again, we want to keep these answers as precise as we can. Calculators often giving us an approximation, which can be misleading in certain problems. So there it is. There's your state of the unit. If you have any more questions, feel free to send me a message. I'll try to make another video for you all, and we'll keep going. Back to solving multi-step equations tomorrow. So have a great night, have a great day, have a great week, and let's get something done in school. Alright, see you.